Welcome to lecture number 33 for ECE 463 Modern Control, Peak Noise and Noise Cancellation. Now, here's the problem. Suppose the system has a disturbance, and the disturbance has a very distinct spectra. Can you take this information into account? So let's start out with types of noise. I've got white noise and pink noise. White noise is Gaussian noise. It's essentially at any given instant, the disturbance has a normal distribution with a mean and a standard deviation. For example, white noise looks like the top curve. If we look at the frequency content is 1. All frequencies are equal weighting, everything's there. If you have white noise, there's no correlation between the disturbance at this time and what it was 10 milliseconds ago, so there's really not much you can do about it. In contrast, if you look at disturbances like wind, the wind right now is highly correlated with what the wind was 10 milliseconds ago. Over an hour, it might change a lot, but for a small instant, there is a strong correlation, meaning that wind is not white noise. Instead, if you look at the spectral content of wind, this is from Friedland, Control System Design. It has a thing called a Dryden spectrum. The spectral content looks kind of like this. If I take white noise and run it through a filter with this gain versus frequency, that's what I get. Again, if I go over a span of say 1 or 2 seconds, there's almost no correlation. But for a brief instant, there's a high correlation. If the wind was blowing strong right now, it's probably going to be blowing very strong 10 milliseconds, 100 milliseconds from now. So what that means is that the wind takes your white noise and runs it through a low-pass filter. And that filter has this gain versus frequency. So for a Dryden spectrum, this is roughly the connection between the disturbance due to wind and white noise. It's a 2-pole low-pass filter, 2 poles at -5, 0 at -0.1, and a gain. I can see what that looks like in MATLAB if I create a random vector. In this case, it's going to be n. N is just randn, white noise for every 10 milliseconds. That's going to be completely uncorrelated white noise, looking kind of like this top graph. Now run it through this low-pass filter, and what the output looks like is something kind of like this. It's going to be different every time you run it because it's random. But you can kind of see there is a little bit of information there. It's not completely white noise. Hence this is called pink noise. Got noise with some color. I can model that by saying, let's take a plant. X dot equals AX plus BU, Y equals CX, here's my input U, and add to it extra states. These are the dynamics of my wind disturbance. It's going to take white noise, feed it into my model for the wind, turn it into pink noise. The pink noise then affects the plant. And in state space, I've got now an augmented system, the plant plus the wind model. The input of the wind is 0, other than just wind disturbance noise. The output of the wind disturbance, CW times XW, affects the plant through the B matrix. And I can see how that works. If I take a gantry system, let's assume I've got a 4th order gantry system. I've got wind adding to the force. That's going to push the cart back and forth. I'm going to use the full state feedback control law to try to hold the position. And my set point is at x equals 0. The code will look like the following. This is just the normal gantry system. I'm going to look at both the position and angle. I've got my wind disturbance. This is one way to do the Dryden spectrum. This is cascade form. There's other forms. That's just what I chose. I've got an observer that's planning ahead for a little bit. My full state feedback, pick your favorite feedback controller. This is one I got. Trying to hold it at the origin. And now what I'm going to do is as I run it, I'm going to have my normal input, Here's my standard normal, mean 0, standard deviation 1, feeding into my wind model. The wind states create a wind disturbance. The wind disturbance gets added into the gantry system. That disturbance is not seen by the state estimator, because if I could know what it was, I could cancel it. What that looks like is the following. So if I run it, here I've got a gantry, I've got full state feedback, trying to hold it at the origin. There is no set point, I'm just trying to set it to 0. The wind is buffeting it, pushing it back and forth. And you can see the effect of the wind on the gantry system. And just pushing it around. The feedback is trying to compensate, but again, you've got wind buffeting it. And if we look at the displacement versus time, that's what's happening with the cart. It's getting buffeted around, pushed back and forth by the wind. So here's a question for you. I have an observer. I could build an observer to determine the plant states. I have an augmented system. I have extra dynamics creating the wind. Suppose I built an observer that included both the wind and the plant. Create an augmented system. In that case, I'll be estimating the plant states. I'll also be estimating the wind states. Can I estimate the wind disturbance from the output and the input? And of course, if this system is observable, then yes, you can. And it makes sense that it would be observable, because if it wasn't observable, then the wind wouldn't have any impact on you and you wouldn't care. So I should be able to tell you the wind, at least part of it. Part of it I can't tell. That's my white noise coming in. That's uncorrelated. Basically, I can't tell you what that is. But part of it is colored. So can I tell you what the plant states are? Or the wind states are. So what I'm going to do is create an augmented system. This is my plant plus the wind states. The wind disturbance affects the plant through the C matrix, through the plant's B matrix. U goes into the plant. The observer is not controllable, or the wind is not controllable. The output, I'm looking at the position of the gantry system, not the wind directly, but again the wind affects the states that I'm observing. So that's the plant and the wind. That is the stop system right here. Let's build a full order observer for the augmented system. So I'm going to estimate the plant states, estimate the wind states, exactly the same as the plant, plus my observer gains. To find H, let's pick your favorite method. I'm going to use LQR techniques, placing very heavy emphasis on the wind states because I want to know what that is. And I don't care too much about the gains. I need to know the wind. So try this. And what you're going to get is the estimate of the wind will be fairly close to what the actual wind is. And back over here. That's kind of what you're seeing. The red line is the wind disturbance. The teal, looks like a teal line, is my estimate of that disturbance. Again, it's a pretty good estimate. So here's another idea for you. If I can estimate the wind pretty accurately, can I just subtract that from the input? So again, if D and DE are the same, D is feeding in, causing my cart to buffet back and forth. If I know what that is, I could subtract it and cancel that disturbance. If I do that, then the cart should no longer be buffeted back and forth quite so much. That's noise cancellation. What that shows up in your state space system is here's your plant, there's your observer. My observer gains H, C, so that's all very standard. This term gets added, that minus BCW. I'm going to take the estimate of the wind, XW estimate times CW, that's right here. subtract it times b, gives it minus sign. What that should do, that should cancel my disturbance. In the simulation, what I do is, again, I'll build my full order observer with the augmented states for the wind disturbance. I'm going to put out the observer states. I know what my estimate of the wind is. I'm now going to subtract that from u. And here's what it looks like. So initially, let's see, where am I? Right here. I'm going to subtract my estimate of the wind times 0. So this is, I'm estimating the wind disturbance, but not doing anything about it. And you can see the cart getting buffeted back and forth. Again, this is just the observer is watching it. It's not doing anything, it's just watching. And trying to estimate the plant states, trying to estimate the wind states. For the full order observer, I'm assuming I measure both position and angle, and I'm using LQR techniques with weightings of 1111, weighting 1000 for the wind states. I want to track those. And here's my output. If I look at the standard deviation of the output, see if we can find MATLAB. There you are. Why is the standard deviation of 0.06? I'll now go back into here. Let's see, where are you? Right here. I'll now try to subtract my estimate of the wind. So I've got the observer states, x6, the augmented sixth order system, times my wind. That's my estimate of the wind. Subtract out that effect from u, and here's what you get. And the wind still has some effect. There's some part of the wind that's not correlated. I can't estimate the part that's not correlated. I can't estimate the part that is correlated. And if I then subtract that out, the impact of the wind is much, much less. And previously, I had a standard deviation of 0.06. Now the standard deviation is 0.01. The standard deviation is to measure the spread. So I've got about 1/6 of the spread. I've reduced the impact of the wind by about a factor of 6. So the result is if you have pink noise, you can predict part of that disturbance with an observer. You can then cancel out part of the impact of that disturbance on the actual system. And this actually is used on wind turbines. The optimal pitch depends upon the wind speed, and the wind is constantly varying. If I could change the pitch before the wind changes, then I could get slightly higher efficiency. But I'm trying to predict the future, and actually you can do that. With the plant and observer, where I'm estimating the wind states, I'm kind of telling you what's going to happen in the future. What's the wind going to be doing? And part of it I can estimate, part of it I can't. The part that I estimate does reduce the impact of the variability in the wind on my system. And that's what we saw with the cart and pendulum system. So that's one thing you can do with peak noise. If you have noise which is not white, which has a certain spectrum, meaning it has some dynamics, I can estimate part of that with an observer and cancel out its effect. That's called noise cancellation. That's lecture number 33 for ECE 463 Modern Control, peak noise and noise cancellation.